Welcome to the Shika Serbu Motor channel. This channel provides easy-to-understand explanations of car mechanisms. The topic of this video is advancements in fuel supply systems. The first Harley-Davidson's carburetor in 1903 was made using a crushed tomato can. As you may know, modern gasoline engines use electronic fuel injection systems instead of carburetors. This video will explain the operating principle and types of carburetors, carburetor operation, and electronic fuel injection systems. The carburetor draws in gasoline by using the airflow that is generated by the engine, and then mixes air and gasoline. The gasoline that is pumped from the fuel tank is accumulated in the float chamber. The air intake flow is accelerated by being passed through the venturi, and it draws gasoline from the float chamber. Carburetors come in different types based on the operation of the venturi and the direction of airflow. In a fixed venturi carburetor, the opening and closing of the butterfly valve controls airflow that passes through the venturi. Most passenger cars used to operate using fixed venturi carburetor. A variable venturi carburetor changes the venturi diameter using a slide valve. These were used in high-performance motorcycles. In a constant velocity type carburetor, the opening and closing of the butterfly valve controls the amount of airflow intake. Due to changing airflow intake, vacuum pressure changes within the air passage. The vacuum pressure moves the slide valve to change the venturi diameter. It was also utilized in motorcycles, but in passenger cars, it was known as the SU carburetor and was used in some sports cars. Downdraft type carburetors, which have vertical airflow, has been used for general passenger cars. The side draft type carburetor that has lateral airflow, used by the famous Weber or Solex, had been integrated into some sports car engines. Let's take a look at the operation of a simple single-barrel downdraft type carburetor. Gasoline flows into the float chamber by fuel pump from the fuel tank. The float chamber has two functions: to accumulate gasoline, and to meter the fuel level. When the fuel level rises, the float floats up and pushes up the needle valve. The needle valve closes the inlet port and stops the flow of gasoline. When gasoline is consumed and the fuel level drops, the float also lowers and opens the needle valve. Then gasoline flows in again until it reaches the specified fuel level. By repeating this operation, the float chamber maintains a constant fuel level. While the engine runs at idle, the throttle valve is completely closed, and a negative pressure is created downstream of the throttle valve. Therefore, gasoline is drawn from the slow nozzle located downstream of the throttle valve. By adjusting the throttle stop screw, which adjusts the fully closed position of the throttle valve, the air volume can be adjusted. Additionally, by adjusting the slow adjust screw, the amount of gasoline that flows can be adjusted. Idle speed can be adjusted by these adjust screws. When the throttle valve opens, a negative pressure is applied to the main nozzle, then the gasoline metered by the main jet is drawn out of the main nozzle. When accelerating, a rich air-fuel mixture is required to obtain sufficient engine torque. When the accelerator pedal is open beyond a certain point, the acceleration pump, which is linked to the throttle valve, injects additional gasoline into the air passage. Near full throttle, the negative pressure in the venturi area is increased, opening the power piston to increase the fuel supply from the main nozzle. During engine startup, closing the choke valve creates a high negative pressure around the main nozzle, resulting in a rich air-fuel mixture. In the 1970s, various devices were added to carburetors to meet the demands of higher engine revs, emission regulations, and ease of driving. To accommodate the higher engine revs, secondary barrels were added to optimize the air-fuel ratio for both low and high engine speeds. For controlling exhaust emissions during rapid deceleration, a slow fuel cutoff solenoid valve and a dashpot were implemented. The slow fuel cutoff solenoid valve closes the fuel passage during rapid deceleration. The dashpot prevents rapid closure of the throttle valve. To enable cruise control functionality, an actuator was added to automatically open and close the throttle valve. To facilitate engine startup in cold conditions, an automatic choke function was added. It closes the choke valve automatically depending on outside air temperature. To meet the demands of emission regulations, an air-fuel ratio feedback solenoid was introduced, allowing the adjustment of the air-fuel ratio based on the residual oxygen concentration in the exhaust gases. In June 1968, the Volkswagen 1600 LE and TLE were equipped with the world's first electronically controlled fuel injection system. The days of mechanical controlling using centrifugal force, vacuum, and spring force in carburetors or mechanical fuel injection systems had come to an end. Yes, the era of electronic control had begun. The electronic control fuel injection system is a device that monitors the engine operating conditions from various sensors and calculates the optimal fuel injection quantity through the ECU, engine control unit, to inject gasoline from the injectors. The basic fuel injection quantity is determined based on the air intake volume, engine speed, and throttle opening. The air intake volume is measured by the mass flow sensor. Until the 1980s, flap-type mass flow meters were commonly used. The airflow pushes the flap and alters its angle. The ECU monitors electrical resistance of the potentiometer and determines air volume. The flap creates a significant intake resistance. From the mid-1980s onwards, hot wire types and Kármán vortex types started to be used. The hot wire type uses a platinum wire that is heated by passing an electric current through it, which is placed in the airflow path. The air intake volume is determined by measuring the electric current flowing through the wire. As the air intake volume increases, heat is drawn away from the wire, causing its temperature to decrease, resulting in a lower electrical resistance and a higher electric current flowing through the wire. Conversely, when the air intake volume decreases, the wire's temperature increases, leading to a higher electrical resistance and a lower electric current flowing through the wire. The Kármán vortex type creates vortices via a pillar in the air passage, and determines the air intake volume by measuring the number of vortices. As the air intake volume increases, the number of vortices also increases, and as the air intake volume decreases, the number of vortices decreases as well. The ECU counts the number of vortices by using pressure pulses. The type of mass flow meter used to measure the air intake volume is called L-jetronic. On the other hand, there was also D-jetronic, which estimated the air intake volume using the intake air temperature sensor and air intake pressure sensor. D-jetronic was adopted to reduce costs and was used in small cars or engines with fewer cylinders. It was also adopted in the Volkswagen 1600 LE and TLE models. The engine speed is measured by rotation sensors installed onto the crankshaft and camshaft. The three types of sensors commonly are used: the magnetic pickup type, the Hall effect type, and the MR, magnetic resistance element type. The magnetic pickup type detects changes in magnetic flux caused by the movement of teeth on a signal plate using a coil, and transmits the signal to the ECU as a rotation signal. A Hall element sensor utilizes the Hall effect. It generates a voltage when an electric current is passing through the element and it is subjected to a magnetic field. Hall element sensors became commonly used as rotation sensors from the late 1980s to the early 1990s. The MR, magnetic resistance element, is a sensor that, like the Hall effect sensor, detects changes in magnetic flux. However, it is capable of more accurate detection compared to the Hall effect sensor. Until the 1990s, the amount of accelerator pedal depression was measured using a throttle position sensor incorporated in the throttle valve body. The accelerator pedal and throttle valve were connected by a wire cable, so when the driver depressed the accelerator pedal, the wire cable would be pulled, thereby opening and closing the throttle valve. In the late 1990s, the throttle-by-wire system was introduced. In this system, the accelerator pedal and throttle valve are electrically connected through the ECU, instead of a wire cable. The ECU detects the amount of accelerator pedal depression and calculates how much engine torque that the driver requires, based on driving conditions. It transmits a signal to the throttle motor for controlling the opening and closing of the throttle valve. At the time of the introduction of the throttle-by-wire system, the signal from the accelerator pedal position sensor ensured reliability by utilizing 3 signals with different output characteristics to verify integrity. Nowadays, 2 signals are used for this purpose. In a wire cable type, a bypass passage is provided to bypass the fully closed throttle valve, and the ECU opens and closes the idle speed control valve to control the amount of air passage for controlling idle speed. In a throttle-by-wire system, the bypass valve is eliminated. The ECU directly opens and closes the throttle valve for controlling idle speed. The ECU energizes the coil of the injector and lifts the needle valve to open it. While the needle valve is opened, gasoline is injected. The ECU has a basic injection quantity map that corresponds to the air intake volume, engine speed, and throttle opening, and it calculates the basic injection quantity based on this map. However, various correction maps such as cold start correction, warm-up correction, acceleration correction, power correction, and exhaust gas feedback control are used to determine the final injection quantity. The basic functionality is similar to a carburetor's, but the electronic control fuel injection system allows more precise and rapid control. In recent years, with stricter emission regulations and demands for fuel efficiency, many additional conditions have been added, leading to further precise and rapid control. In August 1996, Mitsubishi Motors introduced a gasoline direct injection system for the 4G93 engine. Common fuel injection systems inject gasoline into the intake port, but in a direct injection system, gasoline is injected directly into the cylinder. There are advantages to direct injection engines, such as high compression ratio and achievement of lean burn. However, there are also drawbacks, including higher costs and soot accumulation. In the 2000s, it became widely adopted in many engines, and in recent years, some engines combine both port fuel injection and direct injection. Thank you for watching. If you enjoyed this video, please consider subscribing to our channel. We'll see you in the next video.